Okay, good morning, everyone. My apologies for this delay. Welcome to this new edition of the Joint Mathematics Colloquium, which is organized by ICMAT, Universidad Complutense de Madrid, Universidad Autónoma de Madrid, and Universidad Carlos III de Madrid. I am Julio de Vicente from the Mathematics Department here, and together with my colleagues José Conde from Universidad Autónoma and José Ignacio Burgos from ICMAT and Pier Giulio Tempesta from Complutense, who's arriving a couple of minutes late. We are organizing this series of conferences that today take place here in Carlos III. It is my pleasure to present our speaker today, who's Professor Joan Bagaria from Universitat de Barcelona. So a few words to introduce him. Joan actually did not study mathematics, but philosophy in Universitat de Barcelona with a specialization in logic. And after that, then he, as a Fulbright fellow, he moved to the University of California in Berkeley, where he did his PhD in logic and methodology of science in 1991. After that, he returned to Barcelona as an associate professor in different institutions, mathematics department in Universitat Autónoma de Barcelona, economics department in Universitat Pompeu Fabra, and logic and history of philosophy of science department in Universitat de Barcelona. And finally, in 2001, he became a ICRIA research professor, which is the position he has now in the math and computer science department in Universitat de Barcelona. Professor Joan Bagaria's field is logic and set theory, but with applications to other branches of mathematics. He has a large number of publications, not only in the best journals in this area, but also in general journals in mathematics, such as Advances in Mathematics, Transactions of the American Mathematical Society, and other journals. He has supervised nine PhD theses, if I am correct. And he's the director of the Barcelona Research Group in Set Theory and the Barcelona Logic Group. Among other positions, he's in the editorial board of the Bulletin and Journal of the London Mathematical Society. He's been an invited researcher in many prestigious centers around the world. And he was the first president of the European Set Theory Society. And in addition to this, since 2005, he's a scientific advisor for ICRIA director. Well, these are just a few, many of his achievements. In addition to all these activities, he's very active in the dissemination of mathematics to general audiences. And I'm looking forward to his talk. And with that, Joan, the floor is yours, so please.
Thank you very much, Julio. Thank you for this introduction. It's hard to keep secrets nowadays. He got all the information in. Okay, it's a real pleasure to be here. Thank you very much to the organizers for the invitation. I will talk about the higher infinite. What is the higher infinite? Kanamori, in his book called precisely The Higher Infinite, which is the standard textbook on large cardinal theory, he tells us that the higher infinite refers to the lofty reaches of the infinite cardinalities of set theory as charted by large cardinal hypotheses. So what are these large cardinal hypotheses? They are also known as large cardinal axioms. So those are assertions that say such and such cardinal with such and such properties exist. Now it turns out that we call something a large cardinal if it's a cardinal. We're talking about cardinals, but we could also talk about sets. Every set, we are assuming the axiom of choice throughout, so every set has a cardinality. So we are talking about very large sets that have a structure that makes them extremely large. Okay, I will explain this in more detail in a few minutes. And the interesting fact about those cardinals is that they are so large that one cannot prove they exist in the standard system of set theory. Those are Miller-Fraenkel axioms with the axiom of choice, or ZFC. Okay, let me give you some examples of those cardinals. The first one was studied and introduced by Felix Hausdorff more than a century ago. This is the notion of weakly inaccessible cardinal. Cardinal kappa is weakly inaccessible if it's regular. Regular means that we have kappa. It means that you cannot reach kappa in less than kappa many steps. That's regularity. It's uncountable. It's bigger than Aleph 0. And it's a limit cardinal. So it's the supremum of smaller cardinals. Okay? That's the notion of weakly inaccessible. A slightly stronger notion is that of inaccessible, also known as strongly inaccessible. It's the same thing. It's regular, it's uncountable, and it's not only a limit, but a strong limit. So it cannot be reached by the power set operation below, right? So 2 to the lambda is still less than kappa for any cardinal lambda less than kappa. This was studied in the 1930s by Sierpinski, Tarski, and also by Zermelo. Those are the earliest notions of large cardinals. Also in the 1930s, Stanislav Ulam, trying to solve the Lebesgue measure extension problem, of which I will talk about later on, he came up with the notion of measurable cardinal. So what is a measurable cardinal? It is an uncountable cardinal for which there is a kappa additive, non-trivial, two-valued measure on the power set of kappa. So it's an ultrafilter. It's an ultrafilter on kappa, so therefore it's you look at all subsets of kappa, and you have an ultrafilter there, and it's kappa additive. So it means that if you take less than kappa many elements of the ultrafilter, then the intersection is still there. It's still in the ultrafilter. This is one of the most well-known and the most useful notions in large cardinal theory, that of measurable cardinal. Then there's the notion of compact cardinal, also known as strongly compact. This was discovered in the 60s, and this is the cardinal that for which the compactness theorem for the infinitary logic L kappa kappa holds. So the logic L kappa kappa is the usual first order logic, but in which you allow quantification over sets of variables of size less than kappa, and you also allow conjunctions and disjunctions of length less than kappa. Okay, everything else is like in first order logic. And the compactness theorem says that if you have any set of sentences in this logic, in any language, can be huge, if every subset of this set of sentences of size less than kappa is consistent, then the whole thing is consistent, right? That's the compactness theorem. And finally, let me just mention one last example, is Vopenka's principle. This is some odd notion, and I say it's a large cardinal notion. However, there's no mention of any cardinals here. It just says that there is no rigid proper class of graphs. In other words, it says that if you have a class of graphs indexed by all the ordinal numbers, so this is a proper class, then it cannot be rigid. It means that there must be necessarily some graph homomorphism that is not the identity on any of the graphs. So there are two graphs, and you must have some graph homomorphism between them, right? Okay, so I just mentioned these few examples to show you that large cardinals come from different sources. They are formulated in very different ways, and okay, now we know these notions correspond to large cardinals, but we don't know much more about that, or at least in principle. Right, so it's an empirical fact that any statement, and I say natural because whenever I say natural, I mean I want to avoid looking at statements that are artificial, like Gödel's sentence that talks about itself and this sort of thing, right? So any natural statement, any statement ever considered by normal mathematicians, let's say, if it's independent of ZFC, then it is either equiconsistent with ZFC or equiconsistent with ZFC plus a large cardinal axiom. That's a fact. What does that mean? Let me explain this a bit better. So how you take any mathematical statement, how can you measure the strength of this statement? Well, you can use large cardinals in the following way. Suppose that, let's see if I have, so we assume the consistent, con means consistency, and it's always modulo ZFC, so ZFC is the basic theory. Now suppose that we have that the statement phi is consistent. It means we have a model of set theory of ZFC in which this statement holds there. And imagine that we can, from this model, we can obtain another model in which A1 holds. A1 is some statement saying such and such large cardinal exists, right? And conversely, imagine then from the assumption that we have a model of A2, another large cardinal axiom, we can get a model of phi. Then we say that A1 is a lower bound on the consistencies of phi, right? Because phi implies A1, consistency-wise, and A2 is an upper bound. So we have those two large cardinal axioms, A2 and A1, and our statement phi that we are interested in is somewhere between those two. In some fortunate cases, the two large cardinal axioms are the same, and then we get a precise measure of the strength of this statement. And then we know that this statement is equiconsistent with this large cardinal. Okay. Right. Okay, let me give you some examples. Consider the statement that says that every coanalytic and countable set of reals contains a perfect set, contains an empty closed set with no isolated points. Every perfect set has the size to continue, right? So it's known, it's a standard result that every analytic set has this property. But what about the complements of analytic sets, the coanalytic sets? Well, it turns out that this statement that every coanalytic and countable set of real numbers contains a perfect set is equiconsistent with an inaccessible cardinal. So even at this very low level of analysis of the real line, large cardinals already pop in, right? So it's pretty strange somehow. Let's look at another example. There was the original problem that Ulam was working on. So whether there exists a countably additive measure that extends the Lebesgue measure and measures all sets of reals. Of course, it cannot be translation invariant, but in principle it could be the existence of such a measure. Well, the existence of such an extension of the Lebesgue measure is equiconsistent with the existence of a measurable cardinal. And a measurable cardinal is a much larger cardinal than inaccessible. Every measurable cardinal is inaccessible, and below the first measurable, there are many inaccessibles below. But in some cases, we get not only equiconsistency, but we get actual equivalence with large cardinals. For example, the existence of a non-trivial, non-zero homomorphism from the kappa product of the integers modulo finite into Z is equivalent to the existence of a measurable cardinal. And the measurable cardinal is the first kappa for which this happens. This is a famous result of Eda that I will mention later on in more detail. And here's another example. Consider the statement that every full subcategory of a locally presentable category closed under colimits is co-reflective. This is a general statement in category theory that has many applications. Well, it turns out that this is equivalent, outright equivalent to Popenka's principle. And for those interested in category theory, so there's this fantastic book by Adamek and Rositsky called Locally Presentable and Accessible Categories, in which there's a whole final chapter in which you can find many, many different reformulations of Popenka's principle in terms of category theory. So this Popenka principle is a large cardinal principle. It implies the existence of many, many large cardinals, extremely large, but it's a very natural statement in category theory that is used for many people. Okay, so here is a picture of very rough picture of the hierarchy of large cardinals. They line up. That's strange, except here, because this we don't know yet how these cardinals, they should line up, but we don't know yet. There's inaccessible at the bottom. Then here are the measurable. The strong compact are what I call the compact or strong compact. These are the same. Vopenka's principle is somewhere here. And okay, so the fact is that in the last decades, there's been lots of work on this, and now there are hundreds. And I would say almost every week, there's a new paper discovering some new large cardinals somewhere in this hierarchy. So it's a very rich hierarchy, and it's not only linear, but it's actually well ordered. So here are some questions. What is a large cardinal? Because all these notions of large cardinals are very different. They come from different sources, but do we have a definition of what a large cardinal is? Why do they line up? Why do they form this linear hierarchy that is well ordered? Is there a complete hierarchy? Is there any way we can find them all, or we can, arrive to a complete description of the large cardinal hierarchy? And most important, are they true? So we are faced here with what we call an intrinsic issue. Are these large cardinal axioms justified as axioms of set theory and therefore of mathematics? Do these axioms come naturally from the concept of set? Well, to answer this, I want to go to the origin of the investigation of the infinite. Let's go back to Dedekind. Dedekind defined a set to be infinite when it is similar, and similar means is bijectable to a proper subset of itself. Okay? Well, so I would say that according to Dedekind, what makes a set infinite is not its size. It's because it's very big. It's because it is self-similar. So the size is a side effect, because if it's similar, it has to be very large. But the important feature of infinity is not the size. It's the fact that it looks exactly the same as a proper subset of itself. Okay, and recent results show that this is indeed the case. So recent results show, and I will show you why, show that large cardinals are in fact self-similarity properties of the universe of all sets. Let me remind you briefly of what I mean by that. What is the universe of all sets? The universe of all pure sets, I would say, looks something like this. So here in the middle line, this is the backbone formed by the ordinal numbers. So we start with 0, 1, 2, 3, all the natural numbers, then comes omega, and so on. We keep taking successors, we add 1, and at limit stages, we take unions. This is the transfinite sequence of all ordinal numbers. It goes on forever. Now, the universe of all pure sets is built along this ordinal sequence by starting with the empty set, then at successor stages, so going from V alpha to V alpha plus 1, we just take the set of all subsets of the previous stage. So we start with the empty set, we take all subsets of the empty set, all subsets of the subsets of the empty set, and so on, and keep going, right? When we reach a limit, we just take the union. When we reach a limit lambda, we take the union. And this way, we form the whole universe, the set-theoretic universe, also known as the von Neumann universe. He was the first one to describe it this way. I painted light blue here just to indicate that the sets that are somehow describable or definable, even if you allow ordinals as parameters, this is what is known as Gödel's constructible universe. We will go back to that. This is a sub-universe, and in fact, all indicates that it's very small compared to the whole universe, the universe of all sets. Right, so let's look at some of the self-similarity properties of this universe and how do they correspond to large cardinals. Let's look at measurable cardinals first. So remember, measurable cardinal was defined in terms of the existence of a kappa complete ultrafilter on kappa that is non-trivial, non-principal. Well, it turns out that this is equivalent to saying that the whole universe, I've drawn it like this now, can be embedded into some sub-universe. I draw it on the side, but in fact, M is contained in here. And in fact, M is smaller in some sense, even though you can embed the whole universe into it. And you can do it in an elementary way. This means that truth is preserved. So any statement about sets in V that holds in the universe holds about the images of those sets in M, right? And vice versa. Now, what is a measurable cardinal? Well, if this embedding is non-trivial, then there must be a first ordinal that is moved, and it can only be moved up. Now, this is called the critical point. So the critical point of such an embedding is a measurable cardinal. And this is if and only if. So kappa is measurable if and only if is the critical point of an embedding from the universe into some sub-universe M. Okay, that's pretty amazing, right? That something that is a local property of kappa, the existence of some ultrafilter there with some properties, is provably equivalent to saying that the whole set-theoretic universe is elementarily embeddable into some sub-universe, and that this kappa is the critical point of that. Well, given this reformulation of being measurable, one is tempted to come up with the stronger notions, and that's what the set theorists did in the 60s and 70s. There are many notions like this, but that's probably the most important, the notion of a supercompact cardinal. So this is the same as before. Let me just go back to the picture. This is the same as before, but now what we want, or what we require for supercompactness, it's a stronger property. So what we say is that kappa is such that if you pick any level higher, say at level lambda, we can find such an embedding such that kappa is sent above that, so it's sent as high as you want. And not only that, the model M is very similar to V. Very similar means that it's closed under sequences of length lambda. Okay, so it's a technical thing, but it's a strengthening of measurability. And this is called supercompactness. So that's the definition, but I explained what the idea is. Okay, now how much stronger can this get? Well, not a lot, because Kuhnen in 1971 proved a very famous theorem that put an end to this process, right? So how big can M be? Can M be the same as the whole universe? Well, no. There cannot be an elementary embedding that is non-trivial, not the identity, from the universe into itself. That's impossible. It contradicts ZFC. And in fact, there cannot be even an elementary embedding from some level of the form V lambda plus 2 into V lambda plus 2. That's impossible. It's not known if you can have an embedding from V lambda plus 1 into V lambda plus 1. And that's one of the strongest large cardinal assumptions we know of. We don't know if it's consistent. But anyway, because of this, one can look at other notions of large cardinals. Here is an important one again. It's called the extendable cardinal. A cardinal is extendable if it's very simple. So you take any initial segment of the set theoretic universe and you want to embed it elementarily into another initial segment, which has to be bigger. Okay? And kappa is the critical point. That's the notion of extendability, and it turns out that Vopenka's principle can also be reformulated in this way using elementary embeddings. So Vopenka's principle is actually equivalent to saying that if you pick any proper class of structures of any kind, algebraic structures, topological spaces, if they are of the same kind, then you can always find two of them such that they are very similar. Two different ones, but for which you have an elementary embedding from one into the other. Okay, that's equivalent to Vopenka's principle. So these examples show that indeed at least those large cardinal notions can be reformulated in terms of self-similarity, right? So the universe is similar to some sub-universe, or some initial segment of it is very similar to another segment of it, and so on, right? Now, in the last 12 years now, since 2012, I started a new program of reformulating large cardinals in terms of a new reflection principle, or self-similarity principle, if you want, that I call structural reflection. And let me show you what it says. There is a principle that goes back to Cantor. Cantor, he was, besides being a great mathematician, of course, he also was very interested in theology. And he thought that what he called the absolute, which is now we would call the set-theoretic universe, was indescribable. So any property that you could show the universe has, then some small subuniverse, some set, has the same property. So every property of the whole universe is reflecting on some set. So this shows that God is undescribable, because everything, any property you can say about the whole thing is already reflected down at some being, some set, right? That was Cantor's sort of metaphysical or theological idea. But it turns out that this is true. This is a theorem of ZFC. Levy and Montague in 1960-61, they showed that, in fact, if you limit the complexity of the sentences in the logical sense, so a sentence is, I write here sigma n. Sigma n means that you have n alternating quantifiers, existential, universal, and many of them are starting with an existential. That's a way of classifying the complexity of logical formulas. So for every n, you can always find some alpha such that this level of the universe is correct in the whole universe. So anything of this complexity that is true in V, it's already true here. And you can use elements of the alpha's parameters. So truth of a fixed complexity goes back and forth between the whole universe and this initial segment. Right, so what does structural reflection say? The principle of structural reflection says the following. If we fix some class of structures of the same kind and is definable in some way, so here is a set with some relations on it, and we have some formula, and the class C is precisely those structures that satisfy this formula, so this is a definable class of structures of any kind, then we say that the class C is reflected at kappa if for any structure in the class that can be anywhere you want in the universe, then there is one also in the class that is very small, that is below kappa, which looks exactly like it. So there is an elementary embedding from the small one into the big one. Okay? That's what this principle says. But now look. If the complexity, if n is 1, so if the complexity of the definition of the class of structures is very simple, namely it just uses one existential quantifier, then you get this. This is a theorem of ZFC that for all such classes of structures that are sigma 1 definable, if you pick any cardinal kappa that is a fixed point of the Bethe function, namely that V kappa is sigma 1 correct in V, about truths of this complexity, and there are many cardinals like that. There is a proper class of those. Pick any one of those. Well, those cardinals reflect all those structures. And this is a theorem of ZFC. Now, what about sigma 2? So now we look at classes of structures that are definable with two quantifiers. There exists something such as for all, right? Okay. Well, then it's a supercompact. How about 3? Well, that's an extendable. So you see, these notions of large cardinals, supercompactness, extendable, and many more, turn out to be just particular instances or particular examples of a much more general principle that lies behind. And this general principle is this structural reflection principle. All those large cardinals are just particular instances or examples of this principle. And what makes the difference between them is the complexity, the definitional complexity of the classes of structures to which we apply this reflection. Okay, so I'm going a bit fast here, but my point, and this is the last, how about Bopenka? Well, Bopenka turns out that this is the ultimate such principle, right? Because it says that this structural reflection principle holds for any class that is definable, and I don't write the cardinal here because it just says, well, there is some cardinal that reflects it, and in fact, if there is one, there's a proper class of them. All this is equivalent. So Bopenka's principle turns out to be precisely the ultimate sort of reflection principle. Okay, so what is the upshot? The upshot is that large cardinal axioms are indeed natural axioms of set theory because they are equivalent to natural reflection principles, what we call structural reflection, that hold in the set theoretic universe. Okay, now I hope I convinced you that these are natural principles. I don't know if I've convinced you they are true, but in any case, they seem reasonable. Okay, for the rest of my talk, let's see how much time do I have. Yeah. For the rest of my talk, I will show you some examples of the use of large cardinals in different areas of mathematics. Of course, large cardinals have the most impact in set theory itself. In fact, in set theory, large cardinals are the trait of the day. I mean, we use them all the time. We cannot live without them, right? It's what we work with in many situations, and we use them for many results in set theory itself. But I will not talk about this. I will try to show you some examples of applications of large cardinals and the impact of those large cardinals in other areas of mathematics. By the way, if there is any question, just ask me. Get some more. So the first kind of applications will be an analysis in the study of the continuum, the reals. Okay, we know, as a result of Suslin from 1917, that every analytic set of reals, analytic sets can be described in different ways topologically as continuous images of Borel sets, or in a logic way. That's why we use the notation like this. This means those are the sets that are definable with parameters, with real numbers as parameters, by one formula of second order arithmetic with only one existential second order quantifier. Anyway, that's a logic notation for this kind of sets. Analytic sets are definable, and they are very simply definable in second order arithmetic, and this is why we call them sigma 1, 1. Now, all these sets are Lebesgue measurable. However, if we go one step higher of complexity, so if all analytic sets are Lebesgue measurable, so are the complements, the coanalytic sets. How about the continuous images of coanalytic sets? Are they Lebesgue measurable? Well, those are the sigma 1, 2 sets. It turns out that the Lebesgue measurability of sigma 1, 2 sets is independent of ZFC. But in this case, we don't need large cardinals. For example, in Gödel's constructible universe, which is the thinnest universe of set theory, it's the smallest universe of set theory that contains all the ordinal numbers, and it's transitive. I mean, it contains all elements of its elements and so on, right? So that's called the constructible universe. There are counterexamples. There are sets of reals that are continuous images of coanalytic sets that are not Lebesgue measurable. And this is on the one hand. On the other hand, you can have all such sets Lebesgue measurable. For example, if Martin's axiom holds. Martin's axiom is a generalization of the Baire category theorem. It's consistent with ZFC. And if it holds, then every sigma 1, 2 set of reals is Lebesgue measurable. So this is independent of ZFC, but you don't need large cardinals here. But let's go one level higher. Let's go at sigma 1, 3 level. So a sigma 1, 3 set of reals is a set that is the continuous image of the complement of a sigma 1, 2 set. Okay, are these Lebesgue measurable? Well, Shala showed in 1985 that if they are, then aleph 1 or omega 1, which is the first uncountable cardinal, has to be inaccessible in the constructible universe, which means that the universe of sets has to be very large compared to the constructible sets, to the constructible universe. And this is just the fact about these very simply definable sets of reals, whether they are Lebesgue measurable or not. How come the Lebesgue measurability of those tiny sets, very simply definable, affects the whole universe of mathematics? And it does. It implies that the set theoretic universe is very large compared to the constructible universe. Omega 1 has to be inaccessible there. So we have large cardinals popping in. And conversely, Solovay in 1970, he proved that this is a bit, okay, in set theory, there's one fundamental technique that we used all the time, and that's called forcing. What is forcing? Forcing is a technique that was invented, or rather discovered, by Paul Cohen in 1963 to prove the consistency of the negation of the continuum hypothesis. And therefore, he showed that one cannot prove in ZFC the continuum hypothesis. Okay, what is forcing? Forcing, you start with a set theoretic universe and you expand it by adding new sets. Okay? But you have to do it, this technique allows you to do that, but in a very careful way, so that the expanded universe still is a set theoretic universe, still a model of ZFC. But it satisfies new things because you have added new sets there, having whatever properties. Okay. Now there is one such forcing that it's called the Levy collapse. So you start with an inaccessible cardinal, and then you expand the universe by making all the cardinals below countable. So that this cardinal is still a cardinal, so it becomes aleph 1 in the expanded universe, even though it was inaccessible before. It was much, much larger. Right? Now it has become the new omega 1. Now in this model, in this new universe, you look at L of R. What is L of R? It's the constructible universe, but you put in all the real numbers. So this is the smallest universe of set theory in which all real numbers live. Yeah? This is, unfortunately, this is a model in which the axiom of choice fails, because in this model there's no well-ordering of the reals. But what Solovay showed is that in this model, every set of reals is Lebesgue measurable. Not only that, but they have all the usual regularity properties that are enjoyed by the Borel sets. So they have the Baire property, they have the perfect set property, they are Ramsey, they are kappa sigma regular, all the properties that are enjoyed by the Borel sets. Every set in this model has it. In particular, in this model, all the sets, I would say, all analysts work usually with, they all live in this model. So this is a heaven for them, right? You can work in this model, there are no pathologies, everything works fine, everything behaves like the Borel sets. You can be happy with that, right? So, okay, but you need an inaccessible to get this. So a corollary is that the Lebesgue measurability of all the sigma 1,3 set of reals is equiconsistent with the existence of an inaccessible cardinal. But not only, that's not the only impact of large cardinals on sets of reals. In fact, much more is true. If there exist much larger, much stronger large cardinals, like a supercompact, then the theory of the reals cannot be changed by forcing. So you cannot change the theory of what is true about the reals. You cannot change it by expanding the universe. This is fixed. And as a consequence, because of Solovey's theorem, this also implies that every set of reals in L of R has all the regularity properties. So I would like to draw two corollaries here. First one is that the existence of large cardinals, for example, supercompact, but you don't need so much. It's enough to have a proper class of much smaller large cardinals called Woodin cardinals. This gives you essentially a complete theory of the reals. So anything that you can reasonably ask about the reals, about sets of reals, then definable sets of reals, then you have an answer. There's no danger of independence, or you will get a straight answer from large cardinals. And the second corollary is not so good. Well, unfortunately, the existence of large cardinals don't settle everything. There are problems that cannot be settled. For example, the continuum hypothesis, right? Because the continuum hypothesis is not about the reals, it's about sets of reals, and arbitrary sets of reals. So we go one level higher, and their large cardinals are not so powerful so that they can answer all those questions. They don't answer the continuum hypothesis, but they imply there is no definable counterexample. So you cannot find a reasonably definable set of reals that has cardinality strictly between L0 and the continuum. There's no, so in other words, if you're trying to show that the continuum hypothesis is false and large cardinals exist, how are you going to do it? Because you cannot come up with a definable counterexample. So it should be just a pure existence theorem, and that's probably very hard to do. Anyway, let's move on to another area of mathematics. Let's look what happens in category theory and algebraic topology. Just a few examples quickly. Well, let me remind you of some quickly. We say a category is bounded if there is a small full subcategory such that every object in the initial category C is the canonical colimit of the objects in the small one. Now, Isbell proved in 1960 that the category set up, which is the category of sets with all the arrows reversed, this is bounded if and only if there is no proper class of measurable cardinals. So there is at most set many measurable cardinals. In other words, that from some point on, there are no measurable cardinals in the universe. And that is if and only if that's equivalent to the boundedness of this category. But more interestingly is the following. We say that the category is axiomatizable if it is equivalent in a categorical sense to the category of all models of some first order theory with the arrows being homomorphisms. Well, every axiomatizable theory is bounded. This follows from a classical result in logic, the Lowenheim-Skolem theorem. But what is surprising is that the equivalence of being axiomatizable to being bounded, this is equivalent to Vopenka's principle. So Vopenka's principle here is another reformulation of it, another equivalence. It turns out that Vopenka's principle is exactly equivalent to saying that being axiomatizable and being bounded are the same. And here is another application. Yeah, I don't have much time, so probably I will go quickly. Sorry, I cannot define everything, but anyway, so with some colleagues, we proved in 2015, let me go to the second one. We proved that if there is a proper class of supercompact cardinals, then something called the Bausfield conjecture holds. This was a problem that was kind of central in homotopy theory. Was open for several decades, and it was finally settled by Casacuberta, Svenels, and Smith. using Vopenka's principle. So they showed that Vopenka's principle implies that there exist cohomological localizations in the homotopy theory of spaces, also in the homotopy theory of simplicial sets or spectra and so on. We managed to lower that to a proper class of supercompacts, which maybe you're not very impressed by that, but it's really a huge improvement because Vopenka principle is extremely strong. Supercompacts are still strong, but much, much below, much weaker large cardinal hypothesis. Now, the thing is that we don't know if they are necessary. It's not known if Boswell conjecture follows just from ZFC. It could be. I doubt it, but it could be. And this is, shows another phenomenon. It's an example of another phenomenon that happened many times, that people prove things using large cardinals, and then later on, sometimes many years later, they show the large cardinals were not necessary. So the use of large cardinals is useful because sometimes it's an intermediate step before you prove something in ZFC. So you use all this heavy-duty machinery, all these very powerful tools that large cardinals give you. You use that to prove your thing, and then, well, you say, look, I mean, this shows that very likely this is true, because to show that it is false would imply that those large cardinals don't exist, and this is very unlikely. But this can sometimes is an intermediate step to finally proving your result in CFC. Okay, so this may still happen, but we don't know. Okay, let's look now at abelian groups. I mentioned before this theorem of Ada. It's a classical result that if you look at the omega product of the integers modulo finite, there is no non-trivial homomorphism into the integers. Now, what happened with uncountable products? If instead of countable product, omega, you take an uncountable product. Well, Ada showed in 1982 that the existence of a non-zero homomorphism is equivalent to the existence of an omega-1 complete, this means countably complete or sigma complete, non-principal ultrafilter on kappa. If there is such a thing, then there must exist, maybe it's not kappa itself, but there must, the first kappa which has this ultrafilter on it is a measurable cardinal. So the corollary is that the existence of a non-zero homomorphism from the kappa product of the integers modulo finite into Z is equivalent to the existence of a measurable cardinal. And the measurable cardinal is the least kappa for which this holds. Now, to look at the next example in abelian group theory, I need to introduce a new large cardinal notion that was introduced in a paper with Magidor in 2014. That's the notion of delta compact cardinal. So a cardinal is compact, as I defined at the beginning, even only if is kappa compact in this sense. So it means that a kappa is delta compact. Let's look at the case where delta is omega-1, because that's the only case I'm interested in here. So we say that kappa is omega-1 compact if every kappa complete filter on any set can be extended to an omega-1 complete ultrafilter, to a countably complete ultrafilter. Okay? Now it turns out that every compact cardinal is measurable and therefore regular, but the first omega-1 compact cardinal may be singular. This was a very surprising result that we proved, and this showed that it could happen in the model we got. You have the first measurable is strictly less than the first omega-1 compact, which is strictly less than the first compact. So this omega-1 compact notion of large cardinal sits strictly, consistency-wise, sits strictly between the first measurable and the first compact. Okay? Now, let's look at the following example in abelian group theory. Let's look at the torsion class co-generated by an abelian group. This is the class of groups for which there is no non-zero homomorphism into X. This is usually a proper class because it's closed under direct sums. So the natural question is if this class can be generated by Z, namely if we can find groups in the class of size less than kappa that is so that every group in the class is generated by those small groups. And if this happens, we say that the torsion class is kappa generated. Now, what we proved is that in the case of the integers, the torsion class is kappa generated if and only if kappa is omega 1 compact. So this is exactly, this notion of omega 1 compactness gives you exactly the cardinal for which this class is kappa generated. Okay, I have 5 minutes or how? Yeah, maybe a bit more. Okay, I'm finishing now. Okay. So let me show you more consequences. All the examples I will talk about now are about these large cardinals, the omega 1 compacts. Why are those cardinals interesting, or why they are useful? Well, it's because of that. It's because, let's look at, it's a bit of logic, sorry. So let's look at formulas, logic formulas of this kind. So we have one universal quantifier quantifying over second order variables. Each one may have some finite arity, and there are countably many of them. Then we have an existential quantifier quantifying over countably many first order variables. What comes after that is just a formula with no quantifiers. But we allow, it's in this logic, so we allow infinite countable conjunctions and disjunctions, and we allow parameters, both first and second order. Okay, this is a very particular kind of formulas, but it turns out that a cardinal kappa reflects this kind of formula, and I will explain what that means, even only if kappa is omega 1 compact. So that kappa reflects this kind of formulas means the following. Take any structure you want, and take one of those formulas about sets in this structure. Remember, we can talk also about subsets of this structure because we have second order quantifiers. Suppose this formula is true in this structure. Well, then we can always find a substructure of size less than kappa that also satisfies it. Okay, again, we are faced with this reflection principle. So this kind of reflection is equivalent to kappa being omega 1 compact. Well, it turns out that many notions can be expressed in this way. And whenever you find a notion in topology or in algebra or anywhere that can be expressed in this way, then you can prove a reflection theorem. Let's see some examples. Let's look at graphs. We say that a graph is countably chromatic if you can color all the vertices of the graph using countably many colors so that no two adjacent vertices have the same color. That's a coloring, right? And we say it's countably chromatic if you can color the graph this way using at most countably many colors. Well, if kappa is omega 1 compact, then for every graph that is not countably chromatic, there must be a smaller one, smaller than kappa, size less than kappa, that is not countably chromatic. There must be a counterexample of size less than kappa. Let's look at this result now, which solves a very old question in general topology. So we say that the topological space is kappa Lindelof if every open covering has a subcovering of cardinality less than kappa. And of course, Lindelof means omega 1 Lindelof. Right? Okay, now the product of Lindelof spaces need not be Lindelof, and if you take what's called the Sorgenfrey line and you take the product by itself, this is the Sorgenfrey plane, that's a counterexample. But with Magidor, we showed that kappa is an omega 1 compact cardinal even only if every product of Lindelof spaces is kappa Lindelof. So the first omega 1 compact cardinal is the cardinal that gives you the productivity of the Lindelof property. Exactly that cardinal. Okay. So I mean, there are many more examples. These are just a couple of them. Okay, I will, here's another one. It's about non-normality. So this is a more recent result with Gomez da Silva. If kappa is omega 1 compact, then for every first countable non-normal topological space, there is a subspace of cardinality less than kappa, which is also non-normal. So non-normality also reflects in this way. Okay, to finish, I will tell you about one last example. This is about the normal Moore space conjecture. This conjecture asserts that all normal Moore spaces are metrizable. What is a Moore space? It's a regular space which has a so-called development. So there is a countable sequence of covers, so that every point in the space has a local base formed by, you go to each one of those covers, look at all the neighborhoods of the point, take the union, and this gives you countably many new open sets. This is a local base, okay? So of course, every such space is first countable. Every metrizable space is a Moore space, but the converse is not true. All right, so the normal Moore space conjecture was perhaps the most famous problem in general topology of the 20th century. It went on and on for decades, lots of papers written, lots of work done. Finally, in 1981, Nikos reduced the problem to a problem about measure extensions. I will not go into that. And then Kunen showed that if there is a compact cardinal, then this measure extension problem had a positive solution, and therefore this implied the normal Moore space conjecture. So if there is a compact cardinal is consistent, then we get a model in which the normal Moore space conjecture holds. So it's a consistency result. But very surprisingly, and this came out as a real breakthrough, Fleischner in 1982, he showed that you cannot avoid large cardinals. If the normal Moore space conjecture holds, then you get the consistency of measurable cardinals. So you need large cardinals to answer this conjecture, and at least measurable cardinals are needed. Now in my recent work with Gomez da Silva, we showed that you don't need a compact cardinal, just an omega 1 compact cardinal is enough. So this may sound to you a small improvement, but it's the first improvement or the first advancement on this problem since 1982. So it's not easy to get such a better result. So as I mentioned, we get this model in which the first measurable is strictly less than the first omega 1 compact, strictly less than the first compact. So omega 1 compact is a weaker assumption consistency-wise than compactness, and we showed that just assuming the consistency of a weak omega 1 compact cardinal, then we get a model in which the normal Moore space conjecture holds. What is left to do is, of course, to do the converse, and this we don't know yet. So we know by Fleischner that we need at least proper class of measurables, but we don't know if an omega 1 compact cardinal is necessary. All right, so I think I'll stop here. Thank you very much for your attention.
Thank you very much, Juan. We have time for questions. Is there any question? Yes?
Yeah, so maybe it is me that... So maybe it is me that didn't understood exactly. But I think you say that in sigma 1, 2, if we are in Gödel's universe, yes, then there are contact samples to the measuring. Yeah. But then if you add the existence of higher cardinals, yes, then
yes, but the point is that those large cardinals imply the universe is not L. Okay. If there exists a measurable cardinal, the universe cannot be Gödel's constructible universe. It has to be bigger.
Yes, but how a counterexample can disappear?
Because what is the counterexample? In L, you have sigma 1 to definable well ordering of the reals in length omega 1. Oh, sorry. Yeah. In L, you have a sigma 1 to definable well ordering of the reals in length omega 1. And this is it's an easy exercise using Fubini's theorem to show that this gives you a sigma 1 to set that is not Lebesgue measure. Okay. Now, if there is for example, a measurable cardinal, then the universe, we know it has to be much bigger. It cannot be L. Now, in this universe, there is no such a sigma 1 to definable sets of all the reals, because, you know, there are many more reals there. There are many more. So the set of reals is much, much larger, much bigger, right? So even though in L, we have this well ordering and therefore non-measurable set, when we go, if we assume there is a measurable cardinal, then L is very tiny inside the real universe. And in this now real universe where there is this measurable cardinal, there is no sigma 1 2 well ordering of the reals. That's the difference. Yeah, there are many more reals there. Yeah, it's quite surprising, but that's a fact. For example, take the real that codes all the formulas of set theory that, okay, take all the formulas of set theory that are true about the first omega 1 many aleph 0, aleph 1, and so on. Look at those formulas, okay? Now, well, look at those formulas that are true in L, yes? Well, it turns out that if there is a measurable cardinal, yes, there is one single subset of omega that codes all these formulas. So it codes the theory of this, but this subset of omega cannot be in L, because then L would know what is true about itself, and that contradicts Tarski and definability of truth inside the model. Yeah, I mean, it's complicated, but just the existence of a measurable cardinal implies that there are real numbers that are necessarily outside L. Yeah.
More questions? I have a question myself. So you mentioned that there are certain statements that are proven to be true for large cardinals as a first step to later realizing that they are true for ZFC. You've also discussed, problems that are undecidable for large cardinals, so we know they are undecidable for ZFC, or problems that we know they require large cardinals, hence they are undecidable in ZFC. Are there any problems, I don't know, just crazy questions, who are solved by showing that they are false for large cardinals, and hence they are false for ZFC, or this is a strategy that it's easier to show that they are false in ZFC?
Okay, I don't know if I understood your question, but let me say this. So we have ZFC as our base theory, right? So we believe that the existence of an inaccessible or a measurable or even a supercompact, these are statements that we cannot prove in ZFC if ZFC is consistent. If it's inconsistent, we can prove everything. So, but then it's not interesting. But assuming the consistency of ZFC, then we can add those axioms, right? So this gives us stronger and stronger and stronger theories. Okay. Now, if you can show that something cannot be proven from one of these stronger theories, well, much less can be proven from one of the weaker theories. On the other hand, if something we can show it cannot be proven in ZFC, or maybe ZFC plus an inaccessible, right? So how do we show that something cannot be proven? Well, by producing a model of this theory and the negation of our statement. Then we know that this statement cannot be proven in the theory, because if we could prove it, it would be true in all the models, right? Okay, but the fact that it cannot be proved in one of those theories doesn't rule out the possibility that by assuming stronger axioms, you can actually prove it, right? Yeah, for example, we have seen examples here. So in ZFC, we cannot prove that every quanalytic set uncountable quanalytic set of reals has a perfect set, or that every sigma 1,3 set is Lebesgue measurable, right? But we can prove it using well, not directly with an inaccessible, but if we want to prove it directly, we need to assume, for example, a measurable cardinal. So in the theory, ZFC plus a measurable cardinal, every sigma 1,2 set has all the regularity properties. Yeah. So yeah, so it goes one way or the other. Yeah. I don't know if I answered your question.
You did in part, but I was also somehow wondering whether you've shown some results that show that something is true in large cardinals.
Yeah.
And then it was later realized that it was
Yeah.
true in ZFC.
Yes.
Do we have examples of being decidable, being proven to be false for large cardinals as a proof technique to show that something is false for ZFC?
Yeah. In the same way, right? Yeah, if you can show that something is false under the assumption of large cardinals, well, unless you can show that large cardinals are necessary. And how do you show that? Well, you show they are necessary because if you assume your statement, then you can build a model in which those large cardinals exist, right? So, for example, if every sigma 1,3 set of reals is Lebesgue measurable, then we can go to L, and in L, in the constructible universe, we see that omega 1 is an inaccessible. The real omega 1, of course, not the omega 1 of L. Yeah, so yeah, it goes both ways. Yes.
Okay, thank you very much.
Okay.
Are there more questions? Well then, if not, let's thank John again.